So I'm Elvis Dohmatob. I'm a researcher at Meta in Paris. And what I'm going to present is a joint work with Julia Kemp at NYU and at Meta, Yunzhen Feng with a student at NYU, and Arjun Subramonian, sorry, there's a typo on his name, from UCLA and Meta. So my talk is going to be on the mathematics of NORA scaling laws and model collapse. So just to have a feeling of what's my audience, who has heard about NORA scaling laws? Okay, interesting. So it's now very popular. But so we'll be focusing on like where these laws come from. Okay, so these laws were observed a few years ago by people from companies like OpenAI, Anthropic, Google. So they are like empirical observations, like observing trajectories of planets, you know, and it's not quite clear if there's a law like a law of gravitation which governs that. So that's the kind of stuff we'll do in this talk. So just so we are all on the same page. So NORA scaling laws, essentially, there's this observation which kind of governs the performance of large language models or other models when you train them. Yeah, so so you train a model, right, of a certain size. So here, params, for example, number of non-embedding dimensions. It could be some other measure of complexity. Or here, the size of the data set, you know. So you fix a certain model size. So you fix a certain color, okay, and you look at the performance as a function of the size of the data set. So it follows a certain curve. The same with if you fix this data set size and you look at how the test error, the performance evolves as a function of the size of the model. Okay, it seems to follow a law which is described by this equation. So here, T is the data set size, T is a constant, A is an exponent which is also constant, D is a proxy for the number of parameters, learnable parameters in the model. Okay, so I mean, if D is equal to infinity, meaning you consider a very, very large model, and now you're looking at how your error, this irreducible error. So think of this as like the error minus what you would get by if you had the Bayes oracle. So you're looking at how this evolves with T, and you see in log scale, it's a linear, it's a straight line with slope A, okay? So these are empirical observations. Well, so that was a cartoon. This is actually what on real data sets. So it's kind of universal. So for images, text, video, lots of other stuff. It seems to be, so you see all of this. Each point here is an experiment, a huge experiment, okay? So you plot lots of these things, and somehow they seem to conglomerate around a certain ideal line. So think of this as maybe Newton's law or something. And so the whole point here, why this is a law, is that there are no models under this diagonal, at least within the paradigm of so-called transformer-based models. Okay, so this is like an ID curve you cannot go beyond. Now, why are these laws good for? Now, what you should know is that there is a multi-billion-dollar industry around the business of training large language models like GPT, Llama, or Claude, or Gemini, all this stuff. So you think of it as you have an engineering company, engineering team at a company that has a budget of, say, 50 million, no, that's small, that's 1 billion US dollars to train the best possible model you could get, right? I mean, it would be naive to just go and buy a bunch of machines or buy a bunch of data, right? You want to do this kind of optimally. Now, since you know that you're going to have such a dependence between, so you know that this is like a law. Think of this right now. We're going to see why this is true, that is like a law. So this is kind of fixed. Now, if I give you, for a certain number of parameters and a certain data set size, roughly, your size, the size of work you're going to do in terms of compute is T times D. Okay, so you have T sample points, and this is the number of parameters. Okay, so roughly, okay, think of it as a linear model. For example, this is what you are going to have, T times D. So think of T times D, which is like your compute cost, is equal to 2 billion. Another question is, what's the optimal D? So you see that if I fix T times D equal to a constant, I'm on an ISO curve, and then I have an optimal way to eliminate one of the parameters. Okay, so this is what are called compute optimal curves. Okay, So in this for these curves, you fix the budget, the compute budget, which is T times D, and here you see the optimal model size. Okay, so this is how modulo a few details. This is how the business is done. So such laws, if they were actually laws, that's how you use them to optimally allocate resources to train large language models. Okay, large language models are good for this kind of things, but they're also good for other stuff. People have argued that, okay, you can use this whole neural scaling laws business, they are used for other stuff. So for example, you can use them with some theoretical approximations to explain the emergence of skills. Okay, so you have performance, which is varying linearly with model size on a log-log scale. Okay, so you imagine that you would need to maybe multiply the model size by, say, 1,000 to see a little drop in the model error. Okay, so it means that essentially, if you are just maybe increasing your model size by, say, m, then m plus 1, m plus 2, for 1,000 window of 1, you are not going to see anything. And all of a sudden, you're going to see a delta decrease in error. So this, like, you can see this as emergence. And you can actually make this precise. So precisely, as you scale the model, as you scale the data size, at one point, it starts solving tasks it couldn't. Okay, so the model has now sufficient bandwidth to try to extract useful information from the data. And the same way, think of model size and data set sizes as duals of one another. There are things you're trying to extract, There's data coming to you from the world, and you have two ways to extract it. You can say, okay, I'm going to look at a window of size T and get all of the information I could get from it, or I'm going to look at a model of a certain size and see how much information I can extract. By the way, your models you can also see as a kind of an interesting like database. Actually, for the moment, it's not quite clear how large language models are different from just huge SQL databases, which have some other interesting properties. But that's another debate for another day. Okay, so before we get into serious things, are there any questions? Because it's going to be very important for the sequel. Yep.
For your slide where you show the different modalities and their scaling laws, are the slopes the same or similar, or are they different?
I think the exponents are kind of different. Because the exponents are different, but what is important here is that they're all described by essentially lines in log-log scale.
Yeah. I was just curious if they have that universality.
Yeah, they are different. Okay, maybe generally there is no reason a priori why they should be the same. Like maybe video has the same for a certain amount of video. The amount of information you get, like the information rate is different. I mean, there are many things which could make it different. But what is in universality here is the fact that if you stay within the realm of text, maybe the exponent is constant plus some fluctuation, which is not really important. But yeah, very good question. Now, okay, what I've described is ideal situation. So I get data is coming from the same distribution I will see during test time, but this is not what's happening. Maybe 10 years ago, AI models were very bad. Very, very bad, actually. So there was really a distinction between real data and data which was generated, okay? By construction, over time, these models are getting better and better. So by construction, the difference between synthetic and real data is getting more and more kind of blurry, right? So keep this at the back of your mind that, okay, in future, just the question of whether data is real or synthetic is going to be troublesome. It's going to have really serious consequences because the data, it's actually synthetically looks like real data, but only when you look at very, very like the bulk of the characteristics of the data. Now, the very important. So in this scaling laws, so for example, to get to this point, actually, maybe you need to just capture the very, very high level properties of the data, right? But here, in this to follow this law, this ideal law, like deep down, you would need to start capturing the tail of the distribution. And this is where the synthetic data is different from the real data. In the bulk, I mean, it's basically some basic things like how many pixels on an image are of a certain color, these kind of things. But now maybe other very complicated long-range questions are a bit more difficult. So keep that in mind. Okay, so to motivate what is going to be like the heart of this talk, so recently there's been this phenomenon called model collapse. So as I told you, time is going, we have more synthetic data. One could ask, what is going to happen? Here is a cartoon of what could happen. So before I explain this, let me give a cartoon picture, which I don't have on the slide, but I'm just going to explain it verbally. So think of it, so you have a painting from Picasso, you copy it, and you give the copy to your neighbor who copies it and gives to their neighbor who copies it. Can anyone guess what's going to be the final painting? What?
Monet.
No, but like, how is it going to look like? How is it going to look like? Very bad, right? Like SpongeBob or something, right? So this is what's happening here. So you see, you start with MNIS. Okay, so some model kind of figures out, okay, how to generate, so I think here is an autoencoder, but it could be anything. So it figures out how to generate things that look like digits, right? And then you take these generated digits and you fit another autoencoder. And you keep doing that. And this is what you get after, well, 4 steps. You see? So this is like Picasso and this is like SpongeBob, something like that. So this is a cartoon. It's a bit exaggerated, but not too much. Okay, so this is if as time is going on, we don't quite know what is real and what is synthetic data. We are going to get into a regime where data on the internet is going to be a mixture of different things like this. So each unit of data I get from the internet is going to have marginally very, very small value compared to today. Maybe 10 years ago, almost all data on the internet were like real because AI was necessarily very weak. And in future, it's going to be, you're going to have things like that. Okay, why are we talking about this? So as I already mentioned this, right? So essentially, think of this blue curve as the distribution of real data. So you have some bulk stuff, okay, so, and then there's some stuff happening in the tail. So think of it as maybe, I don't know, some properties of some very, I don't know, very strange plants in the Amazon or something, you know. Thinking of it as the very niche data here, and here's kind of bulk. Now, if you do any kind of synthetic data generation where you train a very large model on real data, necessarily it's just going to capture part of this. It doesn't have enough, it's trained on very large amount of data, but it's still finite. To see the things which are deep into the tail, you will need many examples from the tail, and by construction the tail, where if you draw maybe 100,000 examples, you're going to maybe see something once. So you don't really learn anything. Maybe you memorize it and then you eventually flush it out of memory because, you have better things to do. So if you put this blue distribution through an LLM or whatever procedure that you're using to learn what's happening, it's going to capture maybe up to this point or maybe up to this point. Something finite. The whole point now is that if you now sample from this orange histogram, there is no way you could get this stuff, okay? And that is going to be a serious trouble. So, question, how are the current neural scaling laws, paradigms, so Kaplan, Chinchilla, compute optima, affected by synthesized data, and what does this mean for the future of LLMs, ChatGPT from OpenAI? I put something also for Meta, so I'm not just trolling on the others. And you could put many other things there. So, rough plan of this talk, or whatever is left of it. So first part, I'm going to talk about old results and new questions. Okay, I've basically already mentioned that. And okay, since we are doing theory here, I'm going to forget about all this business about LLMs and fix a very serious problem, namely linear regression. And then I'm going to make that a bit complicated to capture the notion of capacity. And then I'm going to give some ideas how one computes, do the theory on this, hoping that it might help it might inspire some other person to do this kind of, how this kind of computation is done. So as I explained earlier, the blue curve is real data. If you train a huge model here to approximate this real data, it eventually captures just a part of it. What happens, the transformation, what happens is that the Kaplan type scaling laws become this. So you see these plateaus. So if we had the blue curve here, we would have this ideal, a Kaplan type scaling law, which is saying that the laws and the number of data points, okay, they scale as a line in log-log scale, okay, because this has been cropped what's going to happen is that beyond a certain point, the data is going to cease to be useful. So you're going to saturate. Okay. Now, if you say, oh, but maybe my model is very big and very so much data, okay, maybe you're here, but still you're going to saturate maybe at some point later, and so on and so forth. Okay. So this is this is like a precise way to characterize this. Henceforth, when I say model collapse, I am concretely going to mean a deformation of an ideal Kaplan type scaling law into something which plateaus eventually. Okay, and yeah, so in some recent work, we basically showed that this model collapse business is just a change in scaling law where essentially you collapse. It's not like you are, because if it were just like a curve with maybe a worse slope, it would still be good. But what is important here is that eventually just becomes horizontal. So there is no, you are spending money here, but nothing is happening. So that's a first result. I should mention here that, okay, I said the Kaplan-like scaling laws were empirical observations that people observed, no? Like you look at stars and you try to, you record the positions and you see maybe there is a law. Okay, this is an observation in a previous work. I'm going to give reference at the end. We had shown that the Kaplan type scaling laws are actually laws, so they are theorems. If you restrict yourself to a broad class of models, which are an abstraction for large language models, but not actually large language models, so they are called associative memories. So this includes things like dense Hopf networks, but other things. Okay, so it's a broad class. So if you think that a transformer is just something that has registers, and so I see a query, I just correlate it with keys, and then it gives me like a way to select values and weight them by this correlation. So if this is what you think a transformer is, then it's an associative memory. And for this kind of models and others, we have proved earlier at ICLR that we have that the Kaplan-like scaling laws are actually laws. They are theorems that you can prove. So if you have a distribution that has long-tail ZipF type behavior like here, you're going to get this. Okay, so building on this, we show that, okay, synthetic data, since I motivated this earlier, corresponds to copying this. This picture gets deformed into something which looks like this. So these are theorems. Okay, the same thing. Okay, sorry, this question?
I saw that last comment was really interesting. So in the associative memory picture, what sets the exponent of the power law?
It's the distribution of the inputs. Yeah, so you think of it like, okay, let me give a picture. So think of it like you're trying to learn a function which maps x to f of x, okay? And all what you see is you see a stream of x, comma, fx. No, I mean, there was one thing you could do, which is actually, one could solve AI by just doing this. You just have a huge table where you record x, comma, f of x. If you saw infinitely many data, as you keep going, you're essentially going to capture everything, right? But you want this table to kind of be of finite size. So this is what constrains the size of this table. And then now you don't want to just record, you want to record maybe not the axis, but maybe the projection of x in some high dimensional space. And this is going to be like an embedding of tokens in the transformer, this kind of stuff. Now, the axes that you are seeing, if you assume they come from ZipF law with exponent alpha, so x is from something which is like that, x to the power minus beta, where beta is greater than 1. Okay, so if you have this kind of stuff, what we have shown is that if you use an associative memory with capacity D, and you see examples from this, then what you are going to get is a scaling law, which looks like that. T to the minus C plus D to the minus C0, where C is 1 minus 1 over beta. And C0 depends on the algorithm you use, but it's also a function of beta. So this is a theorem. So this is Vivian Cabanes, myself, and Alberto Bietti at Flatiron. Alberto Bietti, yeah, Claire, 24, I think. Yeah. So this is in this sense. And it turns out, okay, this is for this. Now, if this is for like classification, if you are in the case of regression, what one should do is to consider, so if you want, it's power law in, power law out, right? Yeah, if you're in regression, you would consider something which is like, I don't know, so X would be from something like that. And now the eigenvalues of that, so the kth eigenvalue of sigma will be like k to the minus beta. With this, you get the same kind of picture. And this is basically saying you have a high dimensional problem, apparently, but what's interesting is happening in low dimension, which basically means that the stuff you're trying to learn, that the data is smooth in some sense. So you need this and some other such a condition on like the thing that generates the data. So by which I mean, so y is f star of x plus epsilon, and x star correlates with the eigenvectors of this, and these correlations are also of the form, I don't know, let's call those correlations c, k. They are of the form k to the minus some delta. You are going to get something similar. Okay, I lost the screen. Who's that? Okay, sorry about that. Okay, thanks for the question. I hope that answered it. Cool. Yeah, so okay, I already explained this. So this is the same stuff. So this is classical, this is known. This is a work from Kaplan and De Vito from 2007, stuff like that. They have been followed up by people like Maloney and others. So for what I just described, the last thing on the board, you have this kind of ideal. You have this kind of. Yeah, this is for this is for isotropic, but I wanted to talk about this. So for the last thing I described, you have this. Okay, so this is test error by sample size. This is the ideal. So it looks like the Kaplan stuff. You can prove this. And now, if you have this synthetic data business, you have, okay, it looks like a Kaplan type curve in the beginning, but it can actually not only plateau, it can actually diverge to infinity. Yeah. Okay, so let's set up the stage for analysis. So, okay, so what's standard training? Let's think about the business of regression. So here I'm going to talk about linear regression, but you could think about this as regression in a feature space. You can think of this as just some concretization for what could be a kernel method, okay? You could consider the kernel method, and the sigma here would be like, I don't know, like an integral operator associated to the kernel, okay? So data is very simple, multiplied Gaussian with covariance sigma, and the labels are linear plus noise. Kind of one of the things that Boris described earlier. Of course, the noise, you want it to be statistically independent with the features, okay? So what you get, typically, is you get ID sample of size n from this distribution. You feed a downstream model W hat on that, and you test on a random fresh sample from the same distribution. Okay? You can replace this by large language model, but this is typically how things are set up. Now, if you do this, well, it's quite simple. I mean, let's consider the scenario where d is less than n minus 1. Then the ordinary least squares estimator, where you can write it this way. You can simplify. What's important here is you have, this is the word you're trying to estimate, plus a random fluctuation, which has a precise, usually has this formula. Now, if you look at, so this is test error, L2 test error on a random test point X. And the outer expectation is because I want to quench the randomness due to the randomness in the training data, the X and Y's. So if you look at this quantity, it's I do a bit of algebra, you get that this is exactly equal to this, which is this. Okay. Now, if D is much less than N, you can forget about the denominator, so you have something like this. Okay. And where this is looking like 1 over n, right? This looks like a scaling law with exponent 1. So this is classical picture, the scaling law, Nova scaling law with exponent 1. So this is the classical picture. Now let's consider what is closer to what happens in real life. So, okay, so you sample data not from the true data distribution, but from some distribution which could be like something you get from the internet. Okay, we're just making things very simple here. And that thing that you got from the internet was itself trained on some previous data on the internet, right? So let's call it X0, Y0. show the same. You form a data. You form a data set D, and now your least squares estimator is this. Okay, so remember, I mean, it's just the same stuff, except that now I've changed my reference point. I had W star here because I got data, training data from the real data distribution. Now I'm getting data from a synthetic data distribution. That's why now I have this, of course, okay? But because this itself is an approximant, I have this plus something, okay? And now if you develop this, we recover our friend plus something new, okay? Now, let's think for why. So this, as n is going to infinity, well, this is going to 0. So everything is happening well. Now this, remember, W hat 0 was a fixed, was more than, maybe it was very huge, but it was trained on a fixed data set size, n0. So as you are scaling up n, things are going down onto a certain point where this is much smaller than n0, and then it's going to plateau. Okay, so this is going to give you that this is what's happening here. Okay, so the different lines are corresponding here to different generations. So you can iterate this process. Yeah. Okay, that's what we have. So, well, okay, that looks like real life, but it's still not real life. So usually, what practitioners have, they don't just have data from W0 hat. They have a mixture of data from W0 hat. The synthetic data, but they also have real data. You know, maybe they bought it. Maybe it's some data they curated, they have in-house. So they have a mixture of this. And one could ask, okay, maybe a mixture of this is going to solve the problem. What we had before was we had 0 samples from the real world. We just had data from W hat 0. What happens if you have a non-trivial mixture of those two? Can you escape collapse? And so for this, to make this kind of a reasonable research question, so the question one is, can we mix real and synthetic data in such a way that we can avoid model collapse and recover the ideal scaling law, okay? And the second question is, okay, do larger models, do they suffer more or less model collapse? Okay, and so I can give you the answer. Yeah, just 1 second. I can give you the answer to the first question already. If you mix naively, you are not going to escape collapse. You can mix iteratively. Maybe I could draw this on the board. So think of it, right? So I have data from W0 hat. So think of it as a point in model space. And this is what I want to get. So I get data from this. If I learn a model, it's going to be somewhere between these two. Because the training data is a mixture from this to this, right? If I stop here, by the way, the length of this chord corresponds to the quality of the synthetic data. If the synthetic data is of high quality, it means it's close to the real world. But if it's far away, I'm going to have a chord, and by learning a mixture, I'm going to just land somewhere in the middle. Okay? And this could be good, bad, and of course, where I land is going to correspond to the proportion of real to synthetic data. Now, of course, now I have this. I can get data from this. I've learned this model, right? If I replace this with this, you see what's going to happen? Right? So if I do this iteratively, you can show under very general condition that you're going to end up here. Of course, the caveat is that for this to work, you need that each time you land like somewhere in the middle. Because if you're landing too close to here, which would happen, for example, if n1, which is the number of real data points divided by n1 plus n2, if this is vanishing, well, you're going to be landing closer to here, right? So you want this to be like 10 to a constant, which is positive. Okay, if that's the case, then you can do this. And of course, the only caveat is that where this basically means you need the quantity of real data to grow to grow alongside your general data set. If you just have a fixed amount of real data and you are scaling the synthetic data, you're going to fail. So you can recover the ID scaling laws, but you have to pay money. Yeah, there was a question by.
Yeah, your result for the tester was only for the under-parametrized case.
You have the same picture for, you have a similar picture for the overparameterized case where D is bigger than N. But the whole point is that synthetic data, with synthetic data, you basically have a new bias variance decomposition where you have the bias plus variance plus an extra term, which is the term which is going to make you flat. I chose the underparameterized simply because we can see that there's a stark difference between I'm going to 0 and now I'm not going to 0. Yeah, but that's a good point. It's we have a result for general case. Okay, so we have 2 excellent questions, maybe. So theoretical setup, once again, real data distribution has some covariance. So we can take the covariance of the features in the real data set to be different from the synthetic data set. But okay, it's going to turn out that doesn't really matter. What really matters is the labeling function in the real world and the labeling function in the synthetic world. You remember, it's basically this chord. This chord here is, well, it's W1 star minus W2 star. This chord, okay? And that's going to be a proxy for quality. Well, everything else is, there's nothing to be said. And your training data set is so your real plus synthetic. Now I fit a model on that, okay? You fit a model on that, train on that. So you get the model and you test on P1. You only test on, we only care on what's happening on real data. So you train on a mixture of real plus synthetic, but you're only interested in how you do well on real. Now let me pause and make a comment now. This could be by design in the sense that this is synthetic data or some data from the internet, and this is data actually paid for and mixed. But this could also be, I mean, I just have data, I don't know what's in the data, right? The data could be a mixture of synthetic and real data. I don't have any control over that, okay? But what's going to matter here is what is the relative size of N1, N2 in all of the pictures we're going to get. Yes, and this is, well, I'm just simply correcting by, I mean, even if God was a statistician, they wouldn't be able to go below that. So I have to subtract that. So we're going to be in the fine setup, kind of close to what was sitting in the middle, in the beginning, sorry. So we are in a scenario where everything is going to infinity, high dimensional. So input dimension, total data set size, amount of real data, amount of synthetic data are going to infinity in a proportionate way, okay? And also for simplicity, I'm going to take the covariance of the features in both real data and synthetic data to be the same. So the only thing that's changing is the way the labels. So what's changing is how the synthetic data generator actually creates labels compared to what are the real labels, okay? And also for analytical concreteness, I'm going to suppose that W1 star is some Gaussian with the same covariance, and the difference is also Gaussian with some covariance, okay? And then of course, the trace of this gives you a measure of how different these two things are. Okay, and for simplicity, I'm assuming that all of these things commute. I mean, we are not interested in what the eigenvectors of these matrices do. So we might as well assume that they are diagonal, marginal, that they commute. Now in vanilla regression, just for some context, I mean, this is what you do, right? So you define, so this is your least squares, this is your L2 square error plus a regularization term. Maybe if we regularize, we can find something which is doing good in terms of model collapse. And of course, the data you see, so it's your design metrics in classical stuff, but because you have two data sets, you need to stack them like this, and your final model gives you this way. So this is just a ridge estimator for W1 star, and it expands this way because I have data from one source, data from another source. Okay? Yeah.
So if you know which data is real and which data is synthetic, wouldn't you want to
Yeah, sure. That's a good point. I'm going to talk about that. Yeah, if you know which data is real, which data is synthetic, that's what I was explaining there. So you can only do this iterative stuff if you know what is real and what is synthetic. So what was the question?
You can assign some weight less than 1. Like
yeah, of course. That's what I meant by iterating. The iteration we're doing here basically corresponds to, instead of looking at this, you look at this stuff with 1 here times alpha plus 1 minus alpha, the same stuff with 2 there. where alpha is between 0 and 1. Is that what you had in mind?
For one term, yeah, for one of these terms, coefficient alpha. I didn't hear what you said, but yes, for one.
Yeah, sure. There's going. I mean, you want to weight these things differently. Yeah. That's what I was describing on the board, but that's a good point. So what I was saying is that if you do this and you choose the alpha optimally, of course, it has to depend on, okay, what's the relative size of N1, N2, and what's the quality, then you get an optimal curve. But what I'm going to say is that if you do this just once, it doesn't work. You're just going to land somewhere in this curve. What is interesting, what is important here is the fact that N1, N2, and all of these things are going to infinity. For a fixed N1, N2, you might get something which looks like an optimal picture, but in this scenario, if you do this just once, actually it's optimal. What's going to be optimal is essentially to discard all of the synthetic data. So the optimal alpha is going to be alpha, which basically discards all of the synthetic data. But if you have fixed N1, N2, the optimal alpha is somewhere in the middle. So maybe you have to draw a diagram. So for fixed N1, N2, there's some alpha which is optimal. And in that regime, the curve looks like that. And the optimal stuff means you have to discard all synthetic data. But you can find the details in our paper, but yeah, good point. Yes, so, okay, with that, yeah, so first result. So we have this representation, E bar plus zeta. So E bar is the classical bias plus variance decomposition of S error, okay? And now we have okay, it has the, well, this is for the experts. So dFn is the nth degree of freedom of the covariance matrix sigma, evaluated at kappa. And kappa is defined by this fixed point equation, okay? And the role that kappa plays, remember all of the matrices we have here, random matrices, okay? Kappa is the stuff that lets you replace these random matrices by their population counterparts. And for that, you need to trade the lambda you have in your regularization with something else, which is kappa. So this is all classical random matrix theory. The kappa lets you compute the resolvent of the empirical covariance matrix. Anyway, so kappa here gives you a full picture of what's the classical bias term and the variance term. Okay? And now there's this new term, which looks kind of interesting. Now let's unpack this new term. So this is classical. The new term has this. So let's look at this. So all of this, from here to here, you don't control this. So this depends on the covariance matrix of the features, where it's just a problem you're trying to solve. Kappa, well, it's kappa depends on lambda in some concrete way. This factor here, so P2 squared, P2 is the ratio of synthetic to total data. So remember, we're in a regime where N2 over N is going to P2, and N is N1 plus N2. This is real data, and this is synthetic data in your training data set. Okay? So now we have a constant here which is proportional to something which depends on this. Okay? Which means if asymptotically you have some proportion P2 of synthetic data, you are going to inherit an irreducible term in your test error, which you cannot push to zero by simply by any other design choices which you have at your disposal. Is this clear to everyone? Cool. Yeah, so this is what we call strong model collapse. It is strong in the sense that any value of P2, no matter how small, okay, is going to lead to an irreducible error in the test, an irreducible term in the test error, which cannot vanish. Nothing here vanishes. This is what you get when you take everything going to infinity in the way I just described. This stays the same. This can go to zero or whatever, as you would do in classical learning. If you have some good properties about sigma and these kind of things, you can have the classical error which is going to zero with sample size, but this is going to just stick. So that's what we refer to as strong model collapse. Meaning that if you just mix naively train real data and synthetic data, you're still going to have model collapse. So hopefully that's strong. Yes, so I mean, I already explained this verbally. So let's just make this concrete. Let's consider isotropic case. Isotropic meaning that we have identity covariance for the features, and the disparity between the labeling in the synthetic and the real data is delta is C squared over D. Now this parameter is chosen just so that when we look at on average, right, the synthetic data gives this label to an input X, and the real data distribution gives this label to the same input, right? And now we look at the difference of these two labels squared, okay? And we take the expectation when X is sampled well from 0 sigma 1, okay? This, for that choice, is going to give you C squared, meaning that C squared is measuring the quality of the data. Okay, that's just so this is less mysterious. And also, if you do that, then you get this. So this is so phi here is D over N. Remember, we have this classical picture where we had D over N scaling law, right? And now we have this extra term which looks like this. Once again, it's bigger than some irreducible stuff. So this can go to 0. For example, if N is much bigger than D, but this is going to stay. As soon as you have a non-vanishing proportion of synthetic data in your corpus. Okay, in terms of diagrams, what does that mean? That means, okay, this is the classical stuff. So here you're looking at, let's see, 1, 2, 3. So this 1 over 1,000. So for each 1,000 real data points, 1 is synthetic. Okay, only 1 is synthetic, and this is corresponding to the quality. Of course, I can say 1 is synthetic, but one could ask, well, if it's synthetic but has high quality, is it really synthetic, right? That's why we have the C's there. The C's are measuring like what's the quality. Now, okay, there are many things to observe. First of all, okay, so it's some classical, but actually this looks like it's straight, but eventually, but very far, it's going to start to plateau. But let's forget about that for now. Just look at 1% of your one. So for each 100 real data points in your data set, 1 is synthetic. I mean, one would expect that it shouldn't really count, right? But in this scenario already, I have model collapse, okay? And if I even have more synthetic data, it's getting even worse. And now, okay, if the data has slightly better quality, the collapse is going to still happen, but a bit later in the Nova scaling curve, and so on and so forth. So for each proportion of synthetic data in synthetic data of a certain quality, C squared, in a data set, you have these scaling curves which are plateauing, maybe soon, later, but they're all going to plateau. So this is what we refer to as a strong model collapse. Now maybe just, maybe just, so how much time do I have?
15 minutes.
Oh, that's like very good. Thanks. Okay, so maybe I could spend 2 minutes to explain what's happened. Yeah, there's a question.
Quick question. So, in your MNIST plots, for example, with digits, it seemed like after the 20th iteration or something of using synthetic data, the examples were really terrible, right? And the model really collapsed, generating like zeros and ones. But from these plots, it just seems like my loss will be still improving, but plateauing at some point, not really getting worse necessarily. I'm just trying to understand what I'm missing here in terms of this kind of simpler model and
Yeah, that's a good point. So you're totally right that, okay, it seems like, okay, for example, we look here, right? It looks like, okay, it's kind of fine. The whole point of this plot is, okay, one could ask, right, okay, hey, now we have 100,000 times more data, meaning that we are looking at this curve here. What I'm saying is that this looks good up to this point, but maybe to get to this level of test error, right, I need this amount of data. So this is the ideal curve, but this is going to do something like that.
Yeah, but it doesn't start like going up, right? It just
Sorry?
it will plateau and not improve anymore, but it will not be.
Oh yeah, sure. Yeah, definitely. So the plateau to me is still okay. I see what you mean. So okay, model collapse is a very new term. So it doesn't have a kind of a concrete written in marble definition. But to me, model collapse, it's a bunch of curves which are all not very good. I mean, so you could think of like mild model collapse, catastrophic model collapse. So I showed some diagrams where this was the ideal and this is catastrophic. So this catastrophic model collapse, things like this, I also call the model collapse. So it's just a definition question, maybe. Okay, this is good for you. Okay, cool, thanks. Other questions? Cool. Okay, so let me say something maybe about things. I mean, isotropic linear regression is not very serious, right? So let's think about things which are kind of close to neural networks. So believe me, Supral, that at least in the NTK regime for some data sets, you can describe what's happening by this kind of thing. So you have same covariance in the synthetic or the train, and so this is the SVD for the common covariance matrix. So we have this traditional two condition, so it's called spectral decay condition, where we assume that the eigenvalues of lambda, so the diagonal entries of D, they scale as j to the minus beta. So something I wrote earlier on the board. And also, there are correlations, the angles, or the cosines of the angles between W1 and the eigendirections of sigma, they also scale this way. Okay, so this is essentially telling you how smooth the function you're trying to learn is with respect to the input. And so we have a bunch of classical constants, and okay, you consider regularization which is going to 0, but a certain rate which depends on how much data you have. And okay, so there's a bunch of constants. Remember, we defined a kappa at one point, which was like the implicit regularization. In this setup, it has this exact formula. And the second order degree of freedom of the covariance matrix is going to be like this. And the U, remember U was this quantity. We had a bias variance decomposition, and there was this U quantity, which was controlling both the bias, the classical bias and the classical variance. So if you give me U and kappa, I know what's the bias and I know what's the variance. Okay, so U is very important. So okay, so in this concrete case, what I'm saying is that in this setup, the U and the kappa are given exactly like this. Okay, and if they are given like that, well, we can do a computation, very classical computation, to show that the variance is like this, and the bias is like this. Okay, so they're all power laws. Now, for concreteness, let's consider the case where there is no variance term. So the labels are deterministic functions of the input. Okay, so the noise term in yi is equal to 0. Then this is the classical picture. So Caponetto and De Vito and other people, this kind of classical learning theory, Kenner methods, all that kind of stuff. This is what you have. Now, because of synthetic data, the presence of synthetic data, this scaling law gets deformed into this plus another scaling term, which is now competing with this. Okay, so what is interesting here in this problem is that, well, if L is well chosen, this is still going to 0. Okay, so what is happening here is instead of something which moves from this to like something like that or like that, it's actually something which does like that. Okay, so it's a slightly slower scaling rate, but still a scaling law which is going to 0. So it's very important, but the whole point, of course, this term has a certain weighting, which depends on, well, what's the quality of the synthetic data and also how much synthetic data you have. And yeah, so this is a generation of all these classical works, and yeah, fits in perfectly with that. Now, I'm not going to be able to get into the details of this, but let's just say this model, it's a very, 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 very simplistic approximation for neural networks. Well, so here you assume that instead of learning in the ambient input space, you are learning in a space given by given by a certain random projection matrix. So here I'm assuming very, very naively that all what a neural network does is it takes inputs and then just projects them into some space of dimension M. Here, given by a random matrix S, would II the entries of variance 1 over D. Okay? So now the dimension of S, so this M here is going to play the role of the model complexity. If M is large, I'm looking at a projection which has many freedoms. So here everything is the same, and we can play the same game. I'm not going into the detail, but now in the scaling diagram, we have, of course, the ratio of synthetic to total data, the ratio of real to total data. We have this input dimension by number of samples ratio, and now we have something new, which controls like a number of neurons per data point. Okay, so we have a new scaling parameter. Now in this setup, you remember last time we had kappa, now we have a bunch of other crazy constants that control what's happening. So we have these implicit constants defined as fixed points of these equations. And once you have those, you have now a bunch of other things. And I say this just to say, okay, now, so in this random projection setting, which is a very, very, very naive approximation for neural networks, but still, we have the same kind of story, a classical bias plus variance decomposition of the test error, plus an extra term, zeta, which is like this. Precisely the same form. Now, the fact that we are in a neural network, whatever, is simply controlled now by this theta here and omega prime. Remember the definitions. See the definition of, say, omega prime. I have gamma here, and gamma here is controlling. Gamma is phi over phi, which is controlling like a number of effective, the effective number of neurons. So we have that. And of course, what's important here is that we have a new, we have an extra term which causes mayhem, and that we cannot reduce by any design choices. This is kind of fixed. Okay, so concretely, what does that mean? This is a classical picture. So I have the bias term, which has the typical double descent curve. Or it has double descent curve. I mean, this was a big deal a couple of years back. But this is the classical double descent curve, this variance curve, and now I have an extra term, okay, which height depends on the quality of the data, okay? And so what this is going to lead to, where you have this. And so one of the things we can see here is the following. So think of the very pale colored curve. So this, okay, meaning I have perfect quality synthetic data, or equivalently all my data is real, okay? In this scenario, you see that what is optimal is to take a very large model, okay? If I want to make the error to be very small, I want to take this as far as possible, okay? But now, if I have synthetic data of intermediate quality, say like 0.1 or 0.5, okay, I still have a U-shaped curve here. It goes up and comes down at a level higher, okay, than whatever was happening in this basin, meaning that now the optimal size is no longer take the model as big as possible, but somewhere in between. So this answers to the question too. You know, we had a bunch of questions. One of which were, are larger models better or worse regarding model collapse? Okay. So I mean, what I'm not saying is that this is what happens on large language models. I'm basically saying it's a solvable scenario where design choices have precise consequences on how you cope with synthetic data. And you can extrapolate by saying, okay, one would expect that, for large language models, the rules of thumb, which were true for real data or kind of clean training data, necessarily don't hold for, you have synthetic data of dubious quality. And we have these. Sorry, how much time do I have? 5 minutes, okay. So I'm going to skip all of this. This is supposed to be a math workshop, so I'm going to go into this just to explain the kind of how we get these kind of pictures, right? Because I mean, there might be some people who are just interested in this stuff and nothing else. So, I mean, the random projections setup, what you have essentially is you can write your estimator like this, okay? If you forget about all the S matrices, you're just in linear regression. It's just rich. Nothing mysterious happening here. And you can decompose the test error. So the test error is this. So I fit a model. I look at prediction on a random input test point minus the true label of that test point, all of that squared. I look at the average over the test point, and then I quench the randomness due to the randomness in the data set. It gives me something. Well, this you can separate because of the structure of these as two terms, B tilde plus V tilde, which you could think of them as pseudo bias and pseudo variance, and they are given exactly like this. And we can decompose this way because the E1 and E2 are noise vectors. They are random Gaussian IID, and they're independent of any other randomness you have in the design matrices or in the weights. So you can decouple this into this. So we have that. And you can further simplify. I mean, because of all the structural assumptions we had, so the rows of the x's were IID Gaussians from 0 with covariance sigma. What else? Gamma was the covariance matrix of W1 star, which kind of tells us what's the structure. Delta is the covariance of the difference of the labels. Okay, so we have all of these things. And yeah, so we can write it that way. And what's important here is we can write this exactly like this. Okay, what's interesting here is that all of the things that appear here, we can write them always as the expectation of the trace of a certain random matrix. So it's always the expectation of a trace of a rational function in the random matrices x1, x2. Yeah, remember, M1 and M2 are given this way. So these are quadratic functions in the design matrices. M is just their sum. And R is this stuff. So it's a rational function in matrices. Okay, so I have the expectation of a trace of a rational function. And once you see this, you just scream random matrix theory. Yeah, so we have these 4 terms, and computing the limiting values of such quantities is the standard business for random matrix theory. And yeah, so specifically, so for example, if we're interested in computing this kind of quantity where we have this, so just a crash course, a 2-second crash course on free probability theory, what you get is the following. So we are trying to compute the expectation of the trace of a rational function in random matrices in the limit where all the dimensions go to infinity proportionally, okay? And so it turns out there's something called the linear tensor, which is an idea from people doing control theory. So the idea is, the matrix which is causing trouble, so we have this matrix, okay? So it turns out that this gigantic matrix, block matrix, 9 by 9 blocks matrix, if you compute the inverse, one of the blocks is exactly equal to that matrix, this matrix, okay? And actually the precise block is the block 1, 5. So we're using the zero-based indexing. So 1 is 0, 1, 5 is 0, 1, 2, 3, 4, 5. So if you compute the inverse of this matrix, the block which is on this entry is exactly equal to that, okay? What is important here is that this matrix depends on our data only linearly. All the blocks are either 0 or constant, or the random matrix ZK or its transpose. So it's a huge matrix, but what's important is that everything is linear, which means you can do classical random matrix theory on this matrix, and it's going to give you information about this. And the way that's done, typically, well, it's now classical work by Mingo and Specia. Title is, I think, free probability theory for large rectangular matrices or something like that. But the whole point is that, so we have this identity, which you can verify, by the way, by doing short complement, but there's actually an algorithmic way to get these so-called linear pencils. You can do using SymPy or mathematical or by hand. It means that if you're looking at, so you remember we're looking at the trace of this quantity, okay? So I mean, the trace is distributive, right? The trace of a block, if I have a huge block matrix, right? If I want the trace of this, it's like I compute the trace of each block of this and take the entry which corresponds to this. So I have this distributive linear property. And so if I form this matrix, which is just the traces of all the blocks of this, right? I can just look at the entry 1/5 of this is going to give me the quantity I want, because I have this identity. Now, so okay, for the next 3 seconds maybe, the progressivity is that you take this huge pencil, and what you do, you see in this pencil, some of the blocks are constants. This constant, this constant, this constant, 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 and the random blocks are these. This is random, this is random, this is random, and this is random. So you can split that matrix into 2 pieces. Constant, random. And now, this should ring a bell, like it looks something like I have maybe random matrix plus lambda identity. In classical random matrix theory, right? You'll be looking at the trace of something like this. And this will be constant, this is random. So that's the analogy you should keep in your mind. But now this is not identity, it's a giant block matrix. So this is why this is called operator value free probability theory, because what you have essentially operators. And okay, the rest of it is like an algorithmic recipe. No need to go into that. But the whole point is that at the end of the day, you end up with a fixed point equation, which is similar to fixed point equation defined in the classical Marcheco-Pastor distribution with in the anisotropic setup. But now it looks like this. Okay, so I am looking for G15, but it's given in terms of the other G's, but by a small number of equations which I can solve, at least implicitly. And of course, there are existence theorems about positive solutions of this, which is covered by the classical theory. I'm not going to go into that. And if you do that, you land up with something like this. And then you obtain that the expected trace of this is given by this precise quantity here, okay? Where E1 is defined as positive solution to some fixed point equation, and P1, well, it's just the ratio of real to total data. And yeah, and the same way you can compute all the other terms in that expression. Yeah. And okay, I think the conclusion, I've mentioned it many times orally, so I'm just going to skip and go here. So this is the relevant work for this presentation if you're interested in going further. Thank you very much, and sorry for going slightly above board.